Okay, so let's Chapter 4, okay? Now we are going to look in Chapter 4, we are looking at relationships between two numeric variables, okay? Oops, let me just slide this out of the way. July 7th, man. I hope everybody had a good weekend celebrating America's birthday and Independence Day. I always insist that we call it Independence Day because every country's got July 4th, 4th of July, but only America has Independence Day, so anyway. Relationships between two numeric variables. Let's talk about that. So in Chapter 3, we looked at just describing numeric variables with, what do we call these things? Like the mean and the median, the standard deviation. What are these things called?
Descriptions of spread.
Oh, okay, so the standard deviation is a description of spread, but the general overarching term for any number that we might use to describe a set of data or a distribution, we would call those what? Numeric summaries? Yes, okay. Numeric summaries, also statistics if it's a numeric summary for a sample of data, right? Maybe it's worth driving this point home, so I'll write it up on the board because I know whatever I write up here, you guys write into your notebooks. So, numeric summaries. These are numbers we use to describe a set of data. Okay. Also called statistics. I'll write this. Okay. When the numeric summaries describe a sample. Okay. Again, what is a sample?
Part of the population.
Yeah, the part of the population that we can actually observe. Okay. Why aren't we just observing the population directly?
It's too big.
It's too big. Okay, so statistics is all about trying to describe the population when you can't observe the population directly. Population's too big. We take a sample, we study the sample. We're hoping the sample represents the population. And then and we draw conclusions about the population based on the sample. Okay, and so in Chapter 3, we looked at numeric summaries for samples of data, and we just looked at one numeric variable. And we looked at measures of center, measures of central tendency, right? And measures of spread or dispersion. So what were the measures of center? So this is all review. Review of Chapter 3. Review of Chapter 3. Okay, so measures of center include mean and the median. Great. Okay, I won't go home crying tonight. Okay, and then what about measures of spread? Yeah, okay, standard deviation, IQR,
Range.
deviation, IQR, and range. Okay, great. And so these are the things that we covered, and there are ways to calculate all of these things. And again, the important thing is that we are using, these are just numeric summaries. These are ways for us to describe a set of data. Okay. Okay. Another way to describe the set of data, we can talk about the shape. Do you guys remember this? How do we describe the shape of a numeric distribution or a numeric set of data?
Right skew, left skew. Symmetrical?
Okay, yeah, so there's one aspect which is symmetric, right skew or left skew. Great. And then, so that's one aspect. What's the other aspect? And it involves the number of peaks.
Bimodal.
Yeah. Okay. Yeah, so we have unimodal and bimodal or multimodal. Okay. So I'm hoping this is all familiar and fresh in your memory. Okay, so we're all good here? Okay, so now that we know how to describe one numeric variable, which is what we learned in Chapter 3, today we're going to learn how to describe two numeric variables and a relationship between two numeric variables. Okay, so it's not like describing one thing and then you just take another thing and you describe the other thing. Okay, we're going to look at two things together and we're going to try to describe the relationship between these two things. Okay, and so today's lesson, and actually in other lessons of the course, we'll look at other relationships, but here we're looking at two numeric variables. Later on we'll look at a relationship between a categorical variable and a numeric variable. Okay, but today we focus on two numeric variables. So, so our first set of data, okay, we went, here, let me just describe. So now we're moving, so this is a review of Chapter 3 right here, but now we're back into Chapter 4. So let me just describe our data set, okay? So our data set, we went and we gathered information on all 50 states, okay? From all 50 states plus DC, okay? And for each state, or each state, we recorded the median age of marriage for women and the median age of marriage for men, okay? Okay. And so, this isn't individual couples, okay? This is just states, all right? And so it doesn't matter whether or not, this was obviously it's from our textbook, so it's from before the Supreme Court decision, but it doesn't matter before, if there was same-sex marriage or no same-sex marriage. It was just, we just said, California, look at all of the, marriage licenses that have been submitted. look at the men, calculate the median age for the men. Look at the women, calculate the median age for the women. Does that make sense? Okay. Go to Ohio. Median age of marriage for men, median age of marriage for women. Okay, so we're not looking at individual couples, we're just looking at each state. What's the median age of marriage for men? What's the median age of marriage for women? Okay, or women and men. So let's think about our raw data table. How many rows does our raw data table have?
One for each set of data that we put in?
Yeah, right. So each subject or each row is what? How many rows do I have? What's that?
Each person.
I have 51, right? 50 states plus DC, right? So if we do it alphabetically, my first row is going to be Alabama, and then we go to Alaska, Alabama, Alaska, Arizona, Arkansas, etc., right? It's interesting how Arkansas is Arkansas, even though it's spelled Arkansas, but anyway, okay. And then we get median age for men, right? Median age of marriage. And then median age of marriage for women. Okay. And I have no idea what these individual numbers were. Okay, I'm just completely making this up. But this is, you can imagine, this is what we have, right? So we have a total of 51 rows, and then we've got 3 columns: the name of the state, and the median age of marriage for men, and median age of marriage for women. Okay? And so, I don't know. Now, let's look this up. Median age of marriage in each state. Let's see. Can Google do it? My internet here in this room is slow. Let's see. Age at first marriage. Do they have it? Wikipedia? Oh, I hate this slow internet connection. That's like the worst, right? Life is super hard. Okay, America's. All they do is America. In the U.S., median age of marriage, first marriage for, I don't know, what is this? Age at first marriage. What do you think it is for the United States? What? For men.
30,
When they get married?
27.
Yeah.
When they get married?
35.
When they get married.
25, 28.
32, 30, 32.
29, according to 2013. And women?
37.
Someone's optimistic about 29 and 27. Wow. I thought it would be younger than that, but oh, here we go. News.mike. What is this? Oh man, too much. Oh gosh, ads. What? Okay, well, I'm just gonna make up numbers here. All right, so we'll say in Alabama it was 25 and 23. I don't know. I'm making these numbers up completely. Okay, so don't get mad at me. And Alaska, we'll say 28 and 27. I don't know. Okay, so anyway, and we're just making things up, right? So, and then we'll say in Arizona, it was 29 and 27, okay? Et cetera, okay? So we gather all of this data for all 50 states plus a DC. Okay, and then we're going to plot this data. Okay, so we're going to make a graph. And so the graph we're going to make is called a scatter plot. So I'm going to copy this table over, but you don't have to because you have the advantage of continuous paper. So okay, and so to plot this, I'm going to create a scatter plot, and I'm sure you guys are familiar with graphing coordinate pairs. Okay, so we'll across the x-axis, I'm going to put women, and across the y-axis, I'm going to put men. And then we'll, I'm just going to make tick marks. I don't know why my numbers suddenly changed from even to odd, but they did. Okay, and so we would plot each of these. And so Alabama, for the women, the number was 23. And for the men, it was 25. So this dot represents Alabama. Is that okay? And then Alaska was 27 for the women and 28 for the men. So this dot here is Alaska. And Arizona, 27 for the women and 29 for the men. So this dot over here is Arizona. Okay. So far so good? I'm hoping this is level. Okay, and so if I continue this and I graph all of the rows in my data table, how many dots am I going to end up on my graph here?
51.
I'm going to end up with 51 dots, right? So I'm going to just pretend to add a whole bunch of dots here. And we would see something that looks kind of like this. Okay? We would have a total of 51 dots. So after graphing all of the data points,
But they kind of grow to the right. Why would they grow in any particular direction?
yeah. So we'll explain all of that, okay? But so I'm just telling you that this is what a graph would look like, and so we'll say after graphing all of the dots, okay, this thing is called a scatter plot. Okay, so after graphing all of the dots, our scatter plot would have 51 data points. Okay, and let me fix this here. And we see a trend. Okay, the dots seem to go in this direction, right? All right, and so what does that mean? So each dot is what? Is a state, okay? So I don't know what state this is, but in this state, okay, the average age for women was what? was 30, and for men it would look like 32 or something like that. And this over here is another state, and this is women gets married at 23, and the men get married at 24 on average. Okay, the median age. So half of the people are getting married younger than that, half of the people are getting married older than that. Okay. So we see a trend, and the dots seem to go in that direction. And so this indicates that states where women are getting married at a later age also have men getting married at a later age. States where women are getting married at an earlier age tend to also have men getting married at an earlier age. Okay, and that's what this plot represents. Okay, so the overall trend is that states where women get married later generally show men getting married later also. Okay, and states where women get married at a younger age generally also have men And again, each dot is a state. We're not looking at individual marriages. Individual marriages, you can have a great disparity between the age of each person. Okay. But overall, this is the trend, okay? All right, and so this kind of trend, where it's going like this is known as a positive association, okay? So let's talk about directions of trend. Okay. Wait, so who asked the question of why are the dots going up towards the right? Who was that?
I got it.
Okay, but it makes sense now?
Yeah.
Okay. So if your dots go in this direction, okay, this indicates positive association, or just the positive direction. And this means data points with large x values tend to have large y values. Okay, and data points with small x values tend to have small y values. Okay, and so that was our states and, whoops, did I say small x values? Yeah, no, that's correct. Okay, so in the previous page, we can say X was age of marriage for women, and Y was age of marriage for men. So whatever you have. Yes?
Can you also say it the other way around? So like data points with large y values will have large x values?
Yes, yes. So it goes both ways, yes. So large y is associated with large x, small y goes with small x, okay? In general, though, okay, with scatter points, it's not as much of an issue, but later on, we're going to be using one variable to make predictions for the other variable, okay? And so usually you say you know the x and you're trying to predict the y. But what you're saying is correct. If large x goes with large y, then that means large y goes with large x, okay? And if small x goes with small y, then small y goes with small x. Okay, and that would be a positive association. And so that's what we saw with the age of marriage across the states. States where people are getting married later. That's what we have. People getting married younger. That's what we've got, okay? All right, so if the dots go like this, this would be known as what? Negative association, right? We know our opposites. Okay. And so with negative association, data points with large x values tend to have what? Small y values. Okay, and data points with small x values tend to have large y values. Okay. So again, we're talking about two numeric variables. So see if you can think of two numeric variables that will have a negative association and your data set that you might be looking at.
High income and starvation rate.
And what are we looking across?
Well, the higher the income, the lower the hunger rate.
Okay, so but I mean, like, what is one line would be a city, a country, a
Lot of
okay.
Maybe like wealth among cities. So like on the x-axis you would have the cities, and then the y-axis you would have the wealth.
Okay, so the x-axis. So you're saying cities.
Or like, I don't know. I
Yeah.
said cities, for example.
Okay, so well, and these are good things to point out because we have to think across these things. Okay, so with that you're saying your x-axis you would have cities, but cities is not a numeric variable. Okay, so it wouldn't work as you have it. But maybe if you changed one of the things to a numeric variable, we might have something like that. If we're talking about households, you don't really have a starvation rate is not really calculated for a household, okay? But maybe across countries, and you wouldn't have, you can't measure income, but you might say like GDP as kind of a measure of prosperity in the country, and so you could say GDP versus I don't know, poverty level in a country, but I think you'll see quite a bit of scatter. Here's a very simple example. Okay, so just imagine you go to a used Honda dealer. Okay, and so you're looking at a whole bunch of. Let's say you're interested in buying a used Honda Civic. Okay, so you're looking at a bunch of different used cars. Okay. So you're looking at used Honda Civics. Okay, and maybe you're looking at like 100 of them, okay, or whatever. So each one, you can look at each car And maybe you look at the mileage and the asking price, or the sale price of the car. And so you'll see, the Honda Civic with 10,000 miles on it, maybe they're asking 20 grand for it. Okay. The Honda Civic with 160,000 miles on it, how much do you think they'll be asking for that? Maybe 8,000. I don't know. I'm making these numbers up. I'm not in the market for a car, so I don't know what these things are. And then you probably see some kind of general trend. Maybe there's a car with 60,000 miles on it, and it's going for, I don't know, 14,000 or something like that. Okay, I don't know. I'm just making things up. So we see an overall trend, cars with high mileage, so high X value, so high mileage, or we might call that large X, have lower prices, small y. And just the opposite, right? Cars with low mileage, small x, have high prices, large y. So that would be an example of negative association. You have a negative association between the mileage and the price. And I limited our data to Honda Civics just because, if we said all vehicles, then you'll have different values. Just you'd see a much greater spread in the values for price, just because different cars are going to be worth a lot, right? You might ask, would you rather have a Honda Civic with 10,000 miles or a Mercedes-Benz with 60,000 miles, right? And so probably the Mercedes-Benz will still have a higher price at 60,000 than this Honda at 10,000 miles. Okay. But if you limit yourself to just one model, you'll probably see a very clear trend between mileage and price. Is that okay? Positive and negative association, okay? And so, we can talk about different graphs and, the data points that we would see. And so you can have quite a bit of scatter in the dots, okay? But this would be, we would call this positive. And, the dots going something like this. This would be negative. What about dots going like this? What do we say here?
Neutral.
Yeah, so it's neither positive nor negative. Here we would say no association, okay? So this is neither positive nor negative. So we would say no association, okay? Same thing applies if our data points look like this. Kind of just it's neither positive nor negative. So same thing here also. And then you also might see data going like this. Okay. And I would say that also applies. It's neither positive nor negative. Okay. Well, I wouldn't say no association here. Okay, so this would be a non-linear association. Okay. Linear means straight line. Okay. Yes.
That's a changing trend, right? Or is this?
Yeah, we're just going to say nonlinear association. Anytime you have a nonlinear association, or just something curving like that, we're just going to say nonlinear. Okay. And so in our class, so in maybe a more advanced statistics class, we would talk about the different kinds of regression. But in our class, we're just going to stick with the simple straight line linear regression. Okay, so our class will only be concerned about kind of these straight line trends where you can kind of fit a straight line. Okay, so these we will only learn about straight lines. Okay, yes.
What about straight up, like a parallel line?
Parallel.
So you go straight up.
Oh, vertical.
Vertical.
Okay, so let's. So that will I will also say would be neither positive nor negative, but let me just write this down. So we will only cover linear relationships. Okay. So let's talk about this hypothetical situation where we have just a straight vertical line. And you don't have to write this into your book, but can I go to the next slide? Are we okay here? Okay, so let's just say we do have data that looks like this. Okay, what does this mean? What is? Let's say I've marked these off. Okay. So what is the value of this data point up here? What are the two? 3 and 10, right? What about this one right here? 3 and 4, and this would be like 3 and 0 or something. I don't know, I'm making things up. Okay, so if we looked at all of our data, what would we see? Yeah, so all of our x variables are like 3, 3, 3, 3, 3, 3, and then our y we would have, a bunch of different ones here, 0 and 5 and 4 and 10 and 1 and 2, things like that. Okay, so if we're trying to talk about the relationship between x and y, can we really say anything right now? No, because we've only have data where x is 3. Okay? So if somebody wants to say large x or small x is associated with large y or small y, we can't say that because we only have data when x is 3. Okay? So it would be as if, we just look around the classroom and we say, okay, how many eyes do you have? And how much money is in your bank right now, okay? And we're trying to say, well, is there an association between the number of eyes you have and the amount of money you have in your bank? Well, right now we can't say anything. Maybe overall, if we could look across all people, we might see some kind of relationship, but that's it's not going to give you a very good model because at best you're going to have either 0, 1, or 2 eyes, okay? And you're trying to make some kind of relationship between how many eyes someone has and some other variable. You're not going to get much predictive power out of it, okay? So, when you only have values when you have x at only one value, you can't really say anything. So right now we would just say no association detected, right? Okay, is that okay? So yeah, anytime you have these hypothetical questions or something, that's fine, but you always want to think, well, what does it mean to have that situation where my dots are going straight up, okay? Because we can think like, oh yeah, dot's going this way, and dot's going this way, and dot's going this way and that way, but what does it mean, right? If the dots are going straight up, that means you only collected data at one x value. Okay, so we have a numeric summary that describes a relationship, okay? And this is called correlation. Correlation, okay. The full name is the correlation coefficient. But if someone says correlation, they're talking about the correlation coefficient, okay? And the symbol is R. All right, just a quick recap. Just test your recap. Pop quiz, not really. Do you remember the symbols for each of the other things we've studied? So what is the symbol for mean of a sample? All right, good. X bar, okay. Standard deviation of a sample? Hey, look at that, S. Sample size? Yeah, all right. It's making me feel good. All right. Okay, so anyway, correlation, we're going to use R. Okay? And R can be any number between -1 and 1, inclusive. Okay? You cannot have an R value bigger than 1. You cannot have an R value smaller or less than -1. Okay? If you get an R equal to 2.3, you did something wrong. Or that's not R. Okay? That's something else. Okay. So if R is positive, it means the two variables have a positive association. Okay? Positive association means what again? Yeah, it goes up that way. Large X goes with large Y, small x goes with small y. Okay? And if R is negative, what do you think that means? The two variables have a negative association, right? Okay. All right. And we're going to continue on here. If R is close to 0, the relationship is weak. Okay, if R is close to 0, the relationship is weak. That means there's lots of scatter in the data. one variable does not provide very good predictive power for the other variable. Okay. And on the other hand, if r is far from 0, the relationship is strong. Okay. There's little scatter in the data. Okay. And one variable can help you predict the other variable. So star, all of this stuff that I've written here, this is all very important regarding our understanding of R. It's okay? Hmm? Yeah. Okay, go ahead and keep writing. I'm going to look up, whoops, sorry here. I'm going to show you some example graphs of different scatter plots and their R values. So R, the correlation coefficient, or also just called correlation for short. Any value between -1 and 1. Close to 0 means it's weak. Far from 0. What does it mean to be far from 0?
1 or -1?
Yeah, far from 0 means R is close to 1 or -1, okay? So you probably don't need to write that down, but you can write it down if you want. R is close to 1 or close to -1.
So when R is 1 and when R is -1, does that mean there's like a 100% correlation?
Yeah, it means that you have perfect predictive power. If you know one variable, you can predict the other one perfectly. And it means there's no scatter. It means they form a perfectly straight line. Okay, and I'll show you that in a moment here. Okay, so is everybody good here? Let me just show you some pictures. Let's go. Okay. So here, can you guys all see this? Are different scatter plots and different values of R. Okay, so here, the dots are going up in this direction, and they're perfectly in a straight line. This has R equal to +1. Okay, here, actually, yeah, if you guys want to copy this into your notes, probably not a terrible idea. Just kind of plotting these in here. Okay. So, straight line, R equals 1, right? Straight line, no scatter, R equals 1.0. Okay? Just a little scatter, okay? Positive relationship. So R is 0.8. And you can see as there gets more scatter, you know, but overall still we would say there's a positive trend, right? You know, you still might say something like that, okay? But here there's no relationship. There's no overall trend. Okay? And all of these over here, no trend. Oops, this one also. No trend. And all of these are all negative trend, right? Negative association. And this is lots of scatter, less scatter, no scatter. Yeah.
Are the negative numbers just set up that way, or should the negative numbers be on the?
Yeah, well, so this, yeah, well, it's just showing from positive to negative. I mean, just these are just for the illustration, okay? Yeah, normally negative numbers go on the left, but they're just showing a bunch of different graphs here, okay? So this is kind of giving you an idea of how correlation, the R value, works when you see a scatter plot, I'm hoping. Okay, and so this one and this one have R equal to 1.0, right? So the steepness or the slope of the line doesn't matter. Here we have a positive trend in that larger x goes with larger y, smaller x goes with smaller y, and there's no scatter, okay? So the steepness does not matter. Okay, it's the amount of scatter. The amount of scatter and the direction matters. Or matter. Okay. The steepness only matters if it becomes perfectly flat, and then you no longer have a positive or negative direction. Is that okay? So let me add a few more things. Just make sure everybody's got everything written down. Yes, me. No. It can be any value. You can have R equal to 0.23479, okay? These are just example ones, okay? But yeah, R can be any value from -1 to +1, any value, okay? Just in these illustrations, they happen to be 0.4 and -0.4 and 8 and -0.8 and things like that, okay? But R can be any value from -1 to +1. Any other questions? Okay. The order, so a few key things, okay? A few key things about R. I'll write correlation, okay? The order of variables does not matter. Okay, so if the correlation between x and y x and y is 0.62, then correlation between y and x is 0.62. Okay, you just need two numeric variables, and if one is x and one is y, and the correlation is this, and you flip them around, the correlation is still going to be the same. Okay. The correlation is not affected if you add the same number to all the values. Or if you multiply the same number to all values. Okay. So let's say we looked at the temperature in Fahrenheit and the number of people at the beach. What kind of trend do you think we'll see? A positive trend, right? If the temperature is high, you'll probably see more people at the beach. If the temperature is low, you'll see fewer people at the beach, okay? If we converted all of the temperatures to Celsius, from Fahrenheit to Celsius, that involves multiplication and adding, okay? We would have to, I think you have to subtract 32 from all of the numbers, and then you multiply it by 5/9. And that's how you convert from Fahrenheit to Celsius, okay? So we're adding or subtracting the same number to all of the Fahrenheit measures, and we're multiplying all of the numbers by the Fahrenheit measures. Would our correlation change? Let's say the correlation between Fahrenheit temperatures and people at the beach was 0.6. Converting it to Celsius doesn't change that correlation. We've added and multiplied all of the numbers to convert it into Celsius, but the correlation, the relationship between temperature and number of people at the beach, is not affected. Okay? So I'll just write example. Converting degrees Fahrenheit to degrees Celsius involves addition and multiplication. But will not affect the correlation. Between temperature and number of people at the beach. Okay. The correlation coefficient, or correlation, is unitless. So, you know, degrees Fahrenheit, degrees Celsius, it doesn't matter. It just talks about a relationship between between the values. Okay, so it doesn't matter if you've got if you're measuring in feet or centimeters or whatever it is, dollars or pennies or euro or yen or whatever it might be. It doesn't matter. The relationship is unitless. Okay. And lastly, correlation applies only, or I should say, correlation is meaningful only for linear relationships. Okay? So correlation is meaningful only for linear relationships. You can calculate correlation. You can calculate R for any two numeric variables. Okay, but the interpretations only work for linear relationships. Okay, so we will we'll pause here. We'll take a 10-minute break, and we'll come back.